Okay, Assalamualaikum warahmatullahi wabarakatuh. Okay, so now we start and continue our topic 4 in part B, analysis of flow in pipes. Okay, so pipe flow analysis. So we look at the pipe flow analysis here. Okay, there are 4 types. Okay, to get using this analysis. Okay, case 1 is to find HF. Case 2, find L. Case 3 to find the Q. And the case 4 is find the D. Okay, parameter that given for these cases is length, flow rate, diameter, and friction head loss. Okay, now we look at the example 4.10 here, case 1 to find the HF. Okay, water flows in cast iron pipe with 305 mm diameter and 305 meter length in speed of 1525 millimeter per second. So calculate the friction head loss. Okay, to calculate the friction head loss, if kinematic viscosity is 1.13 times by 10 power of negative 6 meter squared per second. Okay, the parameter given is length. Okay, the length is given as 305 meter, Q 1525 mm per second, and D is 305 mm. Okay, so this table is based on the data given here. Okay, and use the cast iron pipe. So the cast iron pipe for the E is based on the table Moody chart. Okay, so you get the E is 0.25 mm. Okay, so first you must find the relative roundness here. Okay, E over D is equal to 0.25 divided by 305 mm. Okay, and 0.0008. Okay, and Reynolds number, you get the value based on the Reynolds number. So you put all the value here and you get the 4.11 times by 10 power of 5 here. So you get the turbulent here. Okay, so from Moody chart, so based on the Reynolds number and the relative roughness, so you get from the Moody chart, so 0.019. Okay, so you get the value of F here. Okay, after you get the F, you find the HF using this formula here. Based on this formula, HF is equal to FLV squared over 2GD. So just put all the data here and you get the value of HF, okay, 2.225 meter. Okay, so you just finish that because you just only have to find the HF. Okay, now for case 2 to find L. Okay, a galvanized iron pipe with diameter of 254 meter is used to flow water in horizontal axis at rate of 50 meter cubic per second. Okay, so if the differences of the pressure head is 2 meter, okay, and kinematic viscosity is given as 1.13 times by 10 power of negative 6 here meters squared per second. So determine the length. So the case 2 is to find the length of pipe. Okay, so given E is 0.15 mm. So the data given here is HF. So HF is given as 2 meter and Q is Q is 50 meter cubic per second and D is 2.454 meter. Okay, so look here. So the D is here. Okay, the D, the kinetic viscosity, the Q, and the E here. Okay, and HF. Okay, HF is 2 meter. Okay, pressure 1 minus by pressure 2 specific weight is equal to 2 meter. Okay, so first you must find the velocity here using this formula of velocity and put all the data here and you get the value of velocity. And then using the Reynolds number, okay, put all the value here until you get the Reynolds number here is 2.2 times by 10 power of 7. So you get the 4,000. So the flow is turbulent. Okay. So then you first find the relative roughness. Okay, based on this value 0.00006. Okay. Using the relative roughness here and also the Reynolds number, so you get the F from Moody chart here. So you get the 0.0112. Okay, after you get the so you must use the energy equation based on the pressure 1 minus by pressure 2 divided by the specific weight plus the V1 minus by V2 squared, to G plus Z1 minus by Z2 and HF. So this is 0. Okay, the velocity 1 and velocity 2. Okay, Z1 and Z2, because this is a horizontal, so you get also 0. So the value just only have this value and the HF here. So the HF, we know that 2 meter. Okay, so this one and the HF is the same. So we get the HF is 2 meter, the given here. Okay, so we know that the HF is using this formula. Okay, using the formula and you get the value 2. Okay, so you solve this formula and then you get the length. So the length is 91.3 meter. Okay, so this is case 2. Now we look at the case 3 to find the Q. Okay, so based on this question here, okay, 100 mm diameter and 120 meter length of cast iron pipe, okay, was used to flow an oil and cause 5 meter of energy head loss. So the HF is given as 5 meter. Okay, kinematic viscosity is this value, and determine the flow rate to get the flow rate. Okay, to get the flow rate of oil in the pipe. So given E is 0.25 mm. Okay, so now we look at the solution here. So this is the data given in the question. Okay, first you must assume that all the flow is based on the fully turbulent. Okay, this is only for case 3. Okay, only for case 3, you assume that flow is fully turbulent. So using the try and error solution. Okay, so first you must using the relative roughness. Okay, find the relative roughness. So we get the 0.0025. Okay, so now using the formula, using the head loss formula here, HF here, and then you find the velocity. So the velocity is based on this formula actually from the HF. Okay, so this formula. Okay, and then you use the Reynolds number. So these two formula that you use to find the F. Okay, to find the F new. Okay, and then to find the Q. Okay, so first you try that 0.025. Why we use the 0.025? Okay, so when we assume that fully turbulence, so that's mean in Moody chart, the must have, you must take a value from 0.025 and above. Okay, and maybe you can also use the 0.02 and above. Okay, so you can assume that first trial here you get the F trial is 0.025. Now when you use the F trial here 0.025, you must substitute in the formula of V here. Okay, substitute in 1 here. Okay, and this is 2. Okay, after you get the after you assume that the F trial here 0.025, and you must put the F trial to formula 1 here, okay, to get the velocity. Okay, so then after you get the velocity based on 1.81 meter second, so just put back again the velocity in formula 2 here, okay, to get the Reynolds number. So you get the Reynolds number is 1.81 times by 10 power 4 here. Okay, after you get the Reynolds number here and you use the E over D here is relative roughness is 0.0025, and the Reynolds number here, okay, you must look back again at the Moody chart. So find the friction factor. Okay, so find the friction factor in Moody chart. Okay, you must look at the Moody chart. So you find the new F. So you get the F new is 0.031. Okay, so the 0.031 is not the same as the 0.025 is. Okay, far. So that is not the same. Okay, so the value F trial and the F new you get is not the same here. Okay, so now you do the second trial. Okay, so the second trial you use the F new that you get from trial 1. Okay, so you use the F trial here is 0.031 here. Okay, so using this F trial new here 0.031, so you must put again in this formula. Okay, the velocity formula here, so you get the value of velocity is 1.62 meter per second. Okay, after you get the value here, so you put again in the Reynolds number formula here, so you get the Reynolds number again. Okay, so based on the relative roughness and the Reynolds number here, so you must look at the Modi chart and find the F new. So you get the F new is 0.031. So it's the same as the trial here. Okay, the same. So if the F new is the same here, say this okay. So you just stop at this trial 2 and you use the F new as 0.031. Okay, so use the F 0.031 and you get the velocity is 1.62. Okay, after velocity you get the 1.62, you get the Q. Okay, get the Q based on this formula. So you get the value of discharge flow rates. This is the concept solved to get the Q. Okay, now we look at the example 4.13 here. Okay, so this example here using to get the flow rate also. Okay, so this is to get the flow rate. Okay, the for welded steel pipe, so we use the roughness here, E here is 0.045 mm. Okay, friction loss gradient HF over L. Okay, HF over L is 0.006. Okay, so this is the friction loss gradient based on the given data here. Okay, so if the friction loss gradient is 0.006, so the formula of this is HF over L. So we get 0.006, the given here. Okay, and the diameter is 500 mm. Okay, so you must use to get the relative roughness here based on the relative roughness here, E over D. So E is 0.045 mm divided by 500 mm. So you get the value of relative roughness is 0.00009. Okay, so you get the 0.0009 and find the friction head loss. Okay, using this formula. Okay, so HF divided by L here. So you just put here HF over L and just only have F times by the V2 D times 2G here. Okay, so based on this one, so you just put the value here. HF over L is 0.006. F here and times by the velocity 2. Okay, 0.5 is diameter and 2 times by 9.81. So you get the velocity in this term of F. Okay, so you get this formula in terms of friction factor here. Okay, so assume friction factor F by assuming turbulence quotient. This is also as same and the case 3. So you assume that friction factor F by assuming turbulent flow condition. So you can, okay. So based on the formula here, here, okay, so you can also assume as 0.01. Okay, so the F trial, the assume as 0.018, so is 0.02 actually. Okay, 0.02 actually you can also use the 0.02. So assume based on the friction factor based on the Modi chart here. Okay, based on actually fully rough turbulent flow F level off here. Okay, turbulent here. So you can assume based on the 0.02 and above. Okay, so maybe you can also assume as 0.0 and something here is okay. Okay, so you can just assume, because this is, you can assume, okay, you can assume. So you use, so in this question the use f is 0.0118. Okay, so you just, after you get the f here, so you get the velocity is 2.233 and e over d is the same here, okay, 0.0009. Okay, so Reynolds number is Vd over kinematic viscosity. So you get the 0.5 V here. So in terms of V, so you get the Reynolds number in terms of V. Okay, you use the V here. Okay, you use V here and put 2 here. Okay, and then you get the value here to get the Reynolds number. Okay, so you choose the, look back again at the Moody chart, okay, based on the here. Okay, so you just put back, look back again at the 0.0009 is the relative roughness. Okay, and the Reynolds number here is, you get 1.113 times by 10 power 6 here, you get here. And then just look at the value of f. Okay, so you just look at the, okay, we just go back to the previous here. Okay, you get the Reynolds number here and V over T. So you get the F trial 1 is, okay, F trial 1 is 0.0118. Okay, so because you use the 118 here, the F trial is 0.0118. So check the friction factor F with the correspondent E, D, N over RE. Okay, so if you get the F trial based on the 0.0118, say also, okay, so you just put back again at the volume here, at the V here, so you get the value of 2.120. Okay, then you just put the velocity back again to the Reynolds number here based on the V here, so you get the 1.057 here. Okay, so using the F trial of F, okay, F 0.0118 here, okay, you get the value of the Reynolds number. Okay, so you get the smooth pipes here. Okay, so you get the F trial 1 is you want 0.0118, and then you get the new Reynolds number. Okay, the new Reynolds number is based on the value here. Okay, so you get the value of 0.0131. Okay, actually this is based on the value of the RE here. Okay, so you get the new trial. Okay, for trial and error, okay, tabulate form. So you get the E over D, and we find here. Okay, we just summarize based on this table here. Okay, so we summarize that trial F here. So you get the trial F here. Okay, so you get the velocity based on 2.233. Okay, and Reynolds number here is, you get the 1.113 and you get 10 or 6 here. So check F. So 0.0131. Okay, actually you get the 0.0131. Okay, you get, it's not the same as, okay, actually is, sorry. Okay, so the F trial 1, so 0.0118, you just trial here. Okay, based on trial, based on the F trial, you just assume that 0.0118, you just put here, so you get the value of velocity. Okay, and then put the velocity in this Reynolds number, you get the value of Reynolds number here. Okay, then using the Reynolds number here and over the E over D, so you get the value of F trial. Okay, F trial second is 0.0131. Okay, 0.131. Okay, you use the value of here, okay, the value of 0.0131 here, okay. So this is using, sorry, 0.0131. Okay, so you get the value of velocity here, okay, and then put back to the Reynolds number here, you get the value of RE, okay. So now you just put the new RE power of 5, okay, 1.06, okay, 1. Okay, so you get the value of, okay, 1 point actually at this part here, okay, so you get the assume here, so you get the value, okay, so you get the value, and we get based on this trial here, and so we get, so it's not the same as this one, okay, F trial, if check here is not same as this new, so you get try again, so try this as the new here, so you get the same, so it's okay, so you just okay at this part, so you just stop at this part, so the F is, okay, so F is 0.0131, okay, and the Q is, V is 2.120, so you get the Q is 0.4163, okay, so this is the concept, okay, to get the Q. Now we look at the case 4, okay, so case 4, to find the D, okay, determine the suitable diameter of galvanized iron, okay, based on this data here, okay, so all the data here is give you L, Q, HF, E, and the kinematic viscosity, okay, also use the Reynolds number here, okay, so we know that the Reynolds number based on the Q is to get the V, okay, so you just get in terms of D here, okay, based on the Reynolds number you get this formula in terms of D, okay, you get the 1, okay, so and then you use the HF here, okay, based on the, from this here you just go to here, okay, and based on the D, okay, so the diameter here, so until you get the terms of D here, so you get the equation 2, okay. Now based on the equation 2 here, you just put all the value here, F, okay, and so on until you get the formula here, okay, actually this is the formula till you get the 3, okay, so you this highlight with the green and the green here, so you just use, okay, so you just use the this formula, okay. Now you just using the try and error solution using the formula of green here, okay. Start by assuming a mid-range value of, so this is a mid-range of F, so we just start at the 0.030, okay, so we can assume, okay, maybe you can assume as also 0.025 and 0.020, okay, it's okay, okay, you just assume that in the mid-range value of F, so we try at 0.030, okay. So based on the F trial, you use the formula here, you solve to get the D. So until you get the D is 0.2045. Okay. With the D, you just put again at the formula of the Reynolds number. So you get the value of Reynolds number is this one. Okay. Then with the D that you get 0.2045, so you use to get the E over D here, roughness, okay, relative roughness, so you get the value here, okay. Until you get the E over D and the Reynolds number, you must look at the Moody chart and find the F new. So you find the F new is 0.019, okay. After you get the F new here, so this F new you must use to try as a trial 2, okay, as the second trial. Okay, at the second trial you use the F 0.019 here based on the F new that you get from the first trial. Okay, and then find again the D. You get the D and you get the Reynolds number and you get the new E over D. and we get the F new. So you get the F new is the 0.0195 is the same as the hump, okay? It's the same and near to the 0.019. Okay, so you can stop at this here. So we use the F trial. Okay, F trial. This is F trial second. This is F trial 1. Okay, so use the F trial second is the same as the F new here. Okay, so we stop here and we know that the D is 08186.9. So you get the D is this value. Okay, so this is the concept, the calculation to get the case 1, case 2, case 3, and case 4. Okay, now we look at the minor losses in pipe. Okay, so this is the minor losses in pipe, means losses due to local disturbance of the flow in conduit. Okay, such as change in cross section, projecting, gasket, elbows, valve, and similar items. Okay, using this. Okay, the causes of minor losses. The minor losses are usually confined to a very short length of a flow path. The effects may not disappear for this considerable distance downstream. Okay, so now we look at the minor losses. So the minor losses can be expressed as this value. Okay, HM. Okay, minor losses is HM is equal to KV squared over 2G. Okay, so also can represent them as being equivalent to a certain length of straight pipe expressed in terms of number of pipe diameter ends. Okay, so minor losses also known as HO where it happened, HE loss of head at entrance and so on. So this is minor losses. So the minor losses is using the loss coefficient here K. Okay. So the minor losses is also based on the loss of head of entrance. So this is called the minor losses. The head of entrance here. Okay. Based on the entrance here. Okay. So this is at the entrance. Okay. Flow. Also entrance at the bell mountain. Enter at the square edge flush and the re-enter. Okay. The re-enter here. Okay, so the KE is given. Okay, so all the coefficient of the entrance is given, so no need to worry. Okay, so the bell mounted here, the KE is 0.04. KE for the square edge flush is 0.5 and the KE for entrance is 0.8. Okay, that is the given to you. Okay, the KE. Okay, the KE is actually usually used for the square edge flush here for entrance. Okay. So now we look at the loss of head at submerged discharge here. Loss of head when pipe discharge fluid into filled reservoir or tank. Okay, so we use this formula. Okay, HD. Actually, HD is head loss due to discharge. Okay, KD V2 and over 2G here. When fluid with a velocity is discharged from the edge of the pipe into a closed tank or reservoir which is so large, entire kinetic energy is dissipated. Okay, so this is based on the discharge here. The discharge here based on this. Okay, so the KD, the coefficient of the discharge is 1. So we assume as the 1. So use the KD as the 1. Okay, now we look at the loss of head at a discharge into moving water. So this is using the moving water. So the moving water is based on from the here to the here. Okay, so the when fluid with a velocity is discharged into a body of water moving away in a channel. Okay, so the HD is the V2. Okay, to the channel here V channel 2 and 2G. So this is using the formula. So no need to worry. Okay, all the formula is given in your final. Okay, so discharge loss is equal to the difference between the discharge and the ultimate velocity head. Okay, now we look at the loss of head due to contraction. So this is based on the contraction. So the contraction the here. Okay, so the difference is based on the contraction here. Okay, see here. Okay, happen when pressure drop due to the increase in the velocity and the loss of energy in turbulence here. Okay, so this is the contraction. Okay, so this is possible minimum value of K and the loss coefficient for sudden contraction. So this is based on the sudden contraction. So D2, okay, D2 based on divide by the D1. Okay, actually the D2 is the contraction is from the big diameter to the smaller diameter. So the diameter 2 to the diameter 1. Okay, so the diameter 2 actually as the diameter 1 here. So the diameter 1, this is the diameter 1, this is diameter 2. Sorry, this is diameter 1 and this is diameter 2 here. Okay, so the diameter 2 divided by the diameter 1. Okay, so you get the value coefficient here. Okay, you can get the coefficient here. Okay, if the coefficient is not given to you, so you can find the coefficient here based on the diameter of this contraction. Okay, so you find the from this table. Okay, so if the table given, okay, if not given, the KC is given to you. Okay, now we look at the loss of head due to expansion. So the expansion here, actually expansion is from the smaller pipe diameter to the bigger pipe. So this is called sudden expansion. Contraction, bigger pipe diameter to smaller pipe diameter. Okay, for the expansion from the smaller to bigger. Okay, so this the difference based on the expansion and also the contraction. Okay, for the sudden expansion, so we use the V1 squared over V1 minus by V2 squared over 2G. So there is a rise in pressure because of the decrease in velocity. Okay, but this rise will be even greater if there were not the losses in energy. Okay, so there is excessive turbulence in the flow from C to F, so beyond which the flow is normal. So this is the formula for expansion. Okay, for the gradual expansion, so must also use the kx here. Okay, for the sudden, no kx, so no coefficient k. Okay, for sudden, so we just assume as the 1. Okay, for gradual expansion, so we use the kx here. Okay, the coefficient here to mean. Okay, so actually for the kx is given. Okay, no need to worry. So maybe the kx you can find from the this chord angle or this value here. Okay, but for usually kx is given to you. Okay, so now we look at the head loss due to pipe fitting, loss of head due to pipe fitting. Actually for the pipe fitting, the k here based on the fitting here. Maybe use the fitting of valve, closed return band, short radius elbow and so on. So you must refer to this table so you get the k. Okay, now we look at the bands and elbow. So also based on this, okay, based on the R over D. R is radius, D is diameter. So based on the band of the radius and also the diameter. Okay, so if not given, the table, the graph is given here. So you must refer to this table. If not, the KB is given to you. Okay. Now we look at the example here. Okay. Water flows through a 150 mm diameter pipe at 100 liter per second. So if the pipe suddenly enlarged to 200 mm diameter, find the head loss. Find the head loss. Okay. So V1 Q divided by A1. So we get the value of V1. Okay. And V2 with the same Q but the difference diameter. Okay, diameter is 2 here. So we get the velocity 2 here. Okay. So using the sudden enlargement, so V1 minus by V2 squared over 2G. So you just put the value here until you get the value of the HF due to sudden enlargement. So this is the concept here. So now look at the example 4.16 here. Elevation level for 0.1 here. 0.1 and the 0.2 here. Okay. 0.1 to 0.2 here. So elevation level for 0.1 and 2 is 24 meter and 30 meter respectively. Okay, determine the required air pressure to find the pressure at 1 here. Okay, it's needed to flow 0.013 meter cubic per second of water to 0.2 here. Okay, consider all head losses. So consider all head loss. This is include the HF and also HM. Okay, so because this is mentioned here, consider all head losses. So when consider all head losses, so this must include the HL, head losses is equal to HF plus the HM. So this is mentioned about consider of all head losses. So HL is head losses, must include the friction loss plus the minor loss. Okay, so friction loss is major losses. Minor HM is minor losses. So must consider all that losses. Okay. So look at here. Okay, just given here, given the data here is Z1 24 meter, Z2 is 30 meter, Q is 0.013 meter cubic per second, length and T and so on. Okay. So first you must find the velocity 2. Okay. So velocity 2, so you get the value here is 0.74. Okay. So you get the value of velocity 2. Now using the energy equation or Bernoulli equation, so mass from the point 1 and the point 2 here and plus the HF and the HM, because this is consider all the minor losses. Consider the friction along the pipe HF and consider the minor losses at entrance. Okay. So we know that the P2 is open to the atmosphere, so the P2 is 0. Okay, V1 also 0. Okay, they just have the P1 here. Okay, plus the Z1, okay, plus the V2 squared over 2G plus the Z2, okay. So Z1, Z2 minus by Z1, Z2 minus by Z1, so you get the value, okay. So we know that the HF here, HF using the friction loss formula here, we get the value of here, the value of 1. And HM is using the entrance. So entrance, so we K entrance is 0.5. So use the here 2HM. This is you get the 2. Okay. So using the Bernoulli equation here, okay. So this is only here, just only have P1 and the V2 was this one. Just put all the value here. So this is the HF. This is HM. Okay. Put here back again. So you just get the value here until you get the P1 divided by the specific weight, you get the value of 7.7 meter. Okay. So you get 7.7 meter and times by the specific weight here, so you get the P1 here. Pressure at 1 is 75.537 Pascal. Okay. So you get the value of the pressure 1. Okay, now we look at example 1.17 here. Okay, using from the factory B here and closed tank here. Okay, a factory B conveys water from a closed tank through a pipe here. This is the pipe. Okay, with 150 mm diameter or at rate of 0.1. So given that kinematic viscosity of water is this one. Okay, and pipe friction factor is 0.016. So Ke is given. Okay, Ke is the coefficient of the entrance here. This is Ke. And the Kb. So Kb is the band here. Kb and also the Kb here. Okay, and also the K entrance also here. Ke. Okay, so prove that the flow is turbulent. Energy head losses in pipe to find. Can determine the tank pressure at P1 to get the P1 here. Okay, so now we look at the solution here. Okay, Q1, D, F, and kinematic viscosity. First, you must find the area. Okay, so the area of using the diameter pipe, you get this value. Okay, then you find the velocity. Okay, you get the velocity here. Okay, after you get the velocity, you must find the Reynolds number. So you get the Reynolds number is here. There is turbulence. So this is proven. Okay, so the A is proven that is turbulent. Okay, now we know that HL is HF plus HM. Okay, because this mentioned. Okay, so you must find the HF first. Okay, HF FLV squared over 2GD. Okay, you just F. Okay, F. Okay, F you get from the MOOC chart. Okay, F. Okay, if F not given here, so F is also the F is given here. Okay, so F is given here. Okay, so you just put the F here, put the L, put the velocity squared here. Okay, and 2GD. Okay, and you get the value. Okay, L, actually L is the length of the pipe. So the length of the pipe, the length is 300 times by the 140 and also plus, sorry, 300 plus 150 plus 295. So that's why you just 300 plus 150 plus 295 times by the velocity 2. So you get the value of HF. Okay. To get the HM, so you use the HM here. Okay. So the HM for the minor losses, the also include the KE. Okay, include the KE here. KE here is 0.1 and the K, sorry, this is K outlet to the factory. So the K is 1. Okay, KB is 0.9. Okay, so the include the 0.4 for the K entrance. Okay, K entrance, sorry, 0. This is 0.54. Okay, 0.4. Okay, so the 0.4 here and plus the 2 and K band, KB band for band, coefficient of band 0.9 and plus the KO. KO is outlet, coefficient for the outlet, so we get the 1 here. Okay, and times by the velocity squared over 2g. Okay, so you get the value of 5.2 meters. Now you just plus the HF and the HM, so you get the value here. Okay, so then using the energy equation, okay, so you get the value. Okay, so P1 here and the V1 squared over 2G. Okay, we know that the Z1 is, the value of Z1 is 25. Okay, 25. Okay, and P2 is K here. K plus V2 and Z2 and also the HL here. Okay, so the V1, okay, plus the V2. Actually, the V1 is actually this based on the P1 here. Okay, so the V1 is 0. Okay, and also the pressure here. Okay, this is the through pipe here, the P2. Okay, so they have the pressure 2. The pressure 2 is given as, sorry, the pressure 2 is given, okay, 40 kilopascal. Okay, so pressure 2, this is 0. Okay, so we just only have the pressure here and the Z1 25 and the pressure 2 here and V2 squared here and the Z2 here and the HL. So until you get the value of pressure is this value. Okay. Now we look at the example 4.18 here. This is also the same as the previous example. Okay. To get the flow rate. Okay, based on the from the reservoir here. Okay, through the steel pipe here to the reservoir here. Okay, to reservoir. Okay, so now using the, okay, this is out inlet, okay, A and to the B here. Okay, so HL due to partially closed valve. So ZA minus by ZB is 25 meter. Okay, so gate valve half open though. To get gate, okay, gate half valve to coefficient of the valve is 2.06. Okay, and energy equation between A and B using the Bernoulli equation. So we get the P, okay, the pressure A here, okay, and the VA here, and also the ZA, okay, and the HE minus by HF minus by HB and the HD actually from the, from here, from the right here, based on the, actually this based on the HF plus the HM. Okay, from the right here, so you will just put the left side here, so we just all the negative here, negative of the HE head losses for the entrance. KHF is the friction loss for the along the pipe here, and the HV is for the valve here, and the HD is for the discharge here. Okay, so you just put the value. Okay, now we look at the value here. Okay, the equation for PA here is 0. We know that this is 0. This is also 0. Okay, so they have the ZA. Okay, ZA 25. Okay, and the HE is at the entrance here. Okay, entrance here is 0.5 KE, and also the HV is the valve here. Valve here is 2.1, 2.06, okay, for valve, and the HD is at the one here, is discharge here. Okay, KD, KD is 1. Okay, and this is along the pipe is HF, so you just put the value here, and this is also 0. Okay, and also this 0. Okay, ZA minus by ZB, so we get the 25. Okay, actually ZA, this is ZA. Okay, mention here ZA minus by ZB is 20, this one. Okay, ZA minus by ZB is 25. Okay, so you get the length of the pipe is 100 meter long and is fully turbulent pipe. So we assume that the length of the pipe is 100 meter long and it is fully turbulent pipe flow. So we get the assume that Chata mode, okay, mode chat using the F 0.014. Maybe we use the value here. Okay, we use the F here. Okay, and put the F to this solution here, so you get the value of this one. Okay, then we get the velocity is 6.815 meter per second. Okay, so and then you get the Q is 0.214 meter cubic per second. That's all. So you just assume that, assuming the length of the pipe is, we don't know the length of pipe is not given. Okay, so we assume that is 100 meter, and we assume that the F from the Chatham, okay, the Modi chart, okay, based on the RE, okay, based on the fully turbulent pipe flow, so we assume that the F is 0.014. Okay, so we get the Q here. Okay, this is based on the F is not given, so you assume. Okay, actually usually in your test or in your final, so the F is always given. Okay, so you can find the velocity and then Q. Okay, that's all. Thank you. Assalamualaikum warahmatullahi wabarakatuh. And we have finished our topic 4.